So let's continue. And we just looked at different images in Fourier space, and now is the next thing is to look at how we can do the convolution in the Fourier space. So we have our noisy image, and looking at its Fourier transform, actually it's mostly convenient to look at it in the logarithmic scale because the intensity of the bias is extremely high and the remaining information has very little intensity. So mostly it's useful to look into the logarithm. Now a very simple filter is to select, we see here that there is a lot of noise out here, and at some point we don't see much of the image information. So we could say we have a low-pass filter by just setting a round disk like this, and that would be the multiplication. So if we multiply our image spectrum with this disk, the image looks like this, and then when we do the inverse Fourier transform, it looks like this. So we have a clear noise reduction, but you can see it's a bit grainy. Maybe you have introduced some extra effects. That's an unfortunate effect when you do so strong cutting like we did here. You get ringing effects around the edges, and that can actually, it's not always the ideal thing. So use different filter kernels, and I have now implemented a couple of more. So one would be to use a Gaussian filter. So here I have a symmetric Gaussian filter with some radius. Oops, oh no, oh no, oh no, oh no. Okay, so it seems like I need to go back a bit. So I didn't execute it. Ah, it's coming later. Okay, naja. So now we got it. So, okay. Now we can go back to the slide. So now you can see I have a Gaussian function here instead. And a convenient thing about the Gaussian filter is that the shape is exactly the same in the Fourier space when you look at the bell as such, but the width of it changes. So a strong low-pass filter in real space has a very wide kernel, but as we in Fourier space actually have a very narrow kernel because it more or less only affect the low frequencies. So it's reversed when you apply it in the Fourier space, the width of it. And with that, we can see that we get, again, some blurring effect, not so grainy as before. So that would be one way. We could also do more weird shapes, like this one. So now I'm only focusing on the frequency information along the main axis. And the filtering then looks like this cross here. And what the effect you see now is you have actually quite good denoising, but now you get this textile web effect texture in the images. So this means we can actually cut out very specific frequencies, and that is something we can see on the next slide. For example, not yet. One thing is we can actually tune the filter to the power spectrum of the noise and the image. And with that, we can obtain an optimal filter for the noise conditions and for the image itself. This can even be used for deconvolution. Deconvolution is the process when you try to take out the blurring effect from the image. So you more or less should know what transfer function your imaging system has, and then you can reverse it and make the images sharper. This looks and sounds good in theory. Usually you can't do it that easily. You need a lot of regularizations because that is a very sensitive inversion process. So let's look at a very simple one, a simple implementation. So we have Gaussian noise. White Gaussian noise has a constant level for all frequencies. And then we have the power spectrum of the image, and that is now defining our filter kernel. That means when the power spectrum of the signal is much greater than sigma, then the filter kernel is 1. If it's much less than sigma, then the filter kernel is 0. Now we just need to know the PS. So here we try doing something like that. One way is actually just to compute the power of the Fourier transform of the two images. So that is done by having the Fourier transform of the image multiplied by the conjugate of it. And then we have our power spectrum. And then we compute what variance we have and compute the filter kernel. And the filter kernel then looks something like this. And the filtered result comes out like this. It is still quite blurred, but we have at least taken out the noise. So this would be this histogram before and after, and we see that we have quite a narrowing of the two peaks, and we can even see that there are separate levels within the image. Another very interesting thing about the Fourier transform, now we have worked with essentially symmetric filter kernels, but what you can do is you can also filter orientations with the help of the Fourier transform. So here I have plotted different orientations. We have 0 degree, 30 degrees, 60 and 90. And if you look at the Fourier transform of these, you can see that you have very nicely two dots which have the line across them, which is perpendicular to the frequency of the real space image. So also here with 30 degrees, you can see that now it has tilted, and with 60 degrees, tilted even more, and 90 degrees, you have it flat here. And this is something we can use in order to get rid of rippled structures within the image. And here is quite advanced example of it, where I used a very attuned filter. The original image, we had problem with these stripes that were really introducing ugly ghost effects in the reconstructions of the tomography. So what we did was to look at the Fourier space. Still, it's a bit hard to identify what we are looking at, but after some tuning, we could see that the stripes, they should be along this slightly diagonal line. And for that, we created now a kernel with this shape. And after that, we could actually filter it and suppress quite a lot, not all, but quite a lot of these stripes, and still keep the image intact. And reconstructions after that, you can see that the effect is that with the stripes, you have a lot of cloudy inhomogeneities in the background around the image. And after the filtering, we have a nice clean reconstruction. So that is one way of how you can use these orientation filters to remove some artifacts from the measurement. It could also see that you have a very textured detector. Maybe you're doing measurements through a fiber optic guide, which is a bundle of many fibers. And these fiber structures they somehow interfere with the image information. And if you do the Fourier transform of such an image, you will very clearly see that you have dots which pinpoint the frequencies of the fiber optic guide, and then you can just pick them out, and you have a nicer image afterwards. Of course, again, we have a bunch of Python functions for doing this, and some of them are in SciPy, and others are in also in NumPy. But you can also, I think, you can find some of it also in scikit-image. So, leaving the basic filters and going into scale spaces, and the thing is, the effects we want to filter are usually very high frequency information, and the structures we want to see is mostly more low frequency information. So what we can do is to look at different scales and do the reduction of the noise on different levels, and with that improve the image quality radically. One way of doing it is to use something called wavelets. That's a big theory of its own, but to put it in very short is that we can divide a signal. We have a signal this long. Then we can divide it. One half is giving you the trend, and one is giving you the detail. So we divide the image into one low frequency and one high frequency part. And the good thing is you can repeat this. So then you have the next time you take the trend image and split that one down. And then you can go step by step down in many to get the coarser and coarser image. The idea behind the wavelet transform is from this downscaling, the downscaling is not good as such, but from the downscaling with the help of wavelets, you can actually go back to original again. And that is the fun thing. So we can use wavelets for noise reduction, for analysis. Wavelets are used a lot in seismic analysis when you have seismic signals and want to see different things on the scale, on different scales. Also on heart rate monitoring, you can also use the wavelets to identify specific features in the patterns. You can also use wavelets for segmentation, and you don't see it here now, but compression is also a typical application of wavelets. In particular, the JPEG compression for all the images that we are using is actually based on wavelet theories. It's not the original wavelets anymore, but because it evolved over many, many years. But the original JPEG was based on wavelets. So let's look at our 1D signal with the wavelets. So here we have a classic test signal where we have a sine with some noise on it, and after that a square wave coming in. And when you look at the trend, you can see here that you have the sine is still quite intact, and you also have a nice pulse here, and the detail is just the noise essentially. And if you do that, take the trend again, then you can split it down, and then you still have the sine and still have the pulse, and again a lot of noise. And then we can do it once more. I wouldn't go much deeper because then there is not much information left. And then with the help of this, we can now start doing our filtering. And before that, we actually look at what the wavelet transform looks like on an image. And images are 2D, so we need to have more information. And the idea is that we have one trend image, and then we have a combination of trend and detail in vertical direction and trend and detail in horizontal direction. And in the last corner, we have detail. And with these, we can actually decompose the image into trend, horizontal detail, vertical detail, and diagonal detail. And that then we do the transform again, which brings us up to another image where we can again do a split and so on. And now again, the light is not with us, but we have this test image. And if we wavelet and transform it, say 1, 2, 3 times, we can see here in some of the detail, you can see here the horizontal lines, you can see here the vertical lines. In the diagonal, it's, with this light, difficult to see it. And so how do we use this now for noise reduction? The idea is that we look at the image, and then we say we do a decomposition to some level, and then we do some thresholding and say that all the details that spikes over some threshold is what we want to keep because it has enough energy to actually be an image feature. And after the thresholding, we get this kind of trend, detail. And when we combine the original trend with this detail, we can get a new filtered image out like this. So this is the very basic wavelet filtering, and it's certainly not done this way, but I would probably have to spend like 2 lectures on only this to really cover all the filtering. But I want you to at least know that with wavelets, you can do this kind of filtering, and let's try it on an image. We have a very noisy image, and by doing this kind of thresholding in the detail, you can get here. And one thing that you may notice is on some places we have these small locations of ringing effects, and that's typical when you do when you work with wavelets. And you can also see it, for example, in strongly compressed JPEG images, that you have this ringing effect along the strong edges in the image, and also somewhere else sometimes. But we got at least some nice denoising, so that is one way. Another way is to start using parameterized scale spaces, and then we start using partial differential equations for solving, starting with processes or equations in nature applied on the image. So we have this example where we can use the heat transport equation, which is defined like this. And then we replace the temperature by the image gray level. And by doing this, we can see that we have an, let's see, I'm a bit confused that it's actually so blurred, the original, but okay. Well, there I am. So we have this original image, and then we let this apply this equation for some time iterations, and now it's there it comes. In the beginning, you can see that the image is there, but after a while, you can see how the gray levels are smoothing out and homogenizing. So this equation may be a starting point, but it's not a good solution because in the end, you will just end up with a completely homogeneous image. So what we do is we introduce a function that controls the diffusivity, which in the previous slide here, the K, or kappa, here is a constant. But now, for the image processing case, we replace it by a diffusivity function that controls that the diffusivity is high for some regions, and it's low for other regions. And what would you use for controlling, what information would you use to control the diffusivity and apply this function on? What would be your stopping feature in the image? So, yes? Nope. The thing that we want to control, use to control the diffusivity, are edges. So, looking at the image, you can see that the edge, that is the place where you don't want the diffusivity to continue. And also, so if you have the sample and you have the background, uncontrolled, it will just blur out and come into one. If you, however, set the edges as the control, the stopper, then you only go to that point and it diffuses here and diffuses here, but not in between. So this is what this function is doing. It's actually creating, with the help of the gradient of the image, creates a diffusivity map like this. So in these regions, it will be full-on diffusion. And when you come to the edges, then it's stop. And that is what's used in this case. And from that, we now can rewrite our diffusion equation into using this function with absolute gradient, and then it works fine. And another thing is, as we have seen, the gradient also enhances noise. So what we do as an extra thing is we actually also apply a Gaussian filter to the image before we compute the gradient. And then we only get the nice edge information and not all the noisy stuff. And with that, we now can see in this little movie how the diffusion is working. It's now you can see how the iteration steps. So we are solving the time steps of this equation iteratively until we come to a point where we are happy with the denoising effect. I think I stopped pretty early in this case, and let's go on with another one. Now, during, say, the early 2000s, regularization became a big topic within image processing, and also during late 90s. But the idea is that we want to do some regularization between the noise in the image and some fidelity term. And with that, we can improve the image quality quite a lot. And the bounded variation that we see as BV here is actually the integral over the whole image of the absolute gradient. And that can be used to control in the minimization problem. And the result is that we get something called, for example, total variation 2 filter, and one is called ISS, which stands for inverse scale space. And the equation looks maybe quite ugly, but what we have is, for example, here we have the fidelity term, and then we have some diffusion effect, or actually it's about the curvature, and then we get a little bit extra support from a secondary equation. And this is a very efficient filter which we use. We have actually used it in our group for very many years, very successfully. And here you can see this is a piece of a lung. It's noisy, and I run the filter iterations here for a little while, a little bit too long because I smooth some relevant features. But in principle, you can see the important thing with this filter is that you can see that this contour here is untouched. It's really a very sharp contrast, and that's the idea behind these scale space filters, is that they are edge preserving, and that's a very important thing because you don't want to blur in the process of removing the noise. You can improve the noise ratio by a factor 10 using these filters, without destroying too much of the image information. Non-local means is something that came up, I think 2005 or 6. It's a different approach to doing denoising. And normally, when you do your denoising with convolution, you always work with local averages. What the non-local means is doing, it's looking at the whole image for regions with about the same structure. And those are averaged together. And that has a very good filtering effect. At 2005 it was. And it has been quite popular in many cases. You need a couple of equations for one computing the local sum of all weights, and then you have some weighting function, and these together build up the filtering effect. And if you want to look more into what these parameters do and how it works, there is a notebook just called, I think it's non-local means. I think it's just called non-local means. And there you have a notebook where you can play and see what the different parameters in the non-local means are doing. It has a very good smoothing effect. And you can see here that you really nicely take out the noise. Some cases you get some structures in the difference, but the important thing is that strong, thin lines are preserved, which is not the case when you do the convolution. You can also get this actually with the scale space filters, this effect. The problem with the non-local means is the complex computational efficiency, because it's an n squared again. And I did, let's say, a very primitive implementation and realized for 1,000 voxel, 1,000 by 1,000 voxel large image, it would take astronomical times to compute the filter. There are, however, solutions where you work with small blocks and filter them individually. Then you can speed it up, and there are actually commercial and probably also open source versions which are much faster and can be applied on 3D images. But this is computationally quite heavy, because you have to go through, compare every pixel with every pixel in the whole image. And that takes a little while. So the non-local means in more detail. I have prepared a notebook, and you're of course welcome to take a look at it. And then from there on you can maybe get some ideas how it works and how it's focused on different regions and the data. This is a new piece I have added to the lecture notes. It's about enhancing and analyzing orientation. Until now, we have just looked at filters, seeing that they enhance things, but we can actually use them already for the analysis and get quantitative information. So if you have images like these, in this case I have a ball packing, I have some hair, and I have a peacock feather. Here you can see very distinct, clear structures. You have the round edges, also the boundary here. Here you can see that there are some preferential directions, but it's not really, you can see it by eye that, okay, here is something in that direction, there is something in that direction. The peacock feather has a major direction in the diagonal, but it also has straight lines going out along the axis. So with the eye, you can clearly see these has these orientations, you can pinpoint it, but how do you tell how to see it, the computer, and put values on it? So the first thing would be to take a look at the gradients. And here we can see the gradient in the x direction, then we can see the vertical lines, also very nice in the hair and the peacock feather. It's not so easy to really determine if what is vertical and not. Then with the Y derivative, you can see that you see more the horizontal side of it, also in the hair, but the peacock feather almost look the same. So it's not so direct easily to tell anything from these. The Fourier transform could also tell us directions, as I showed with these lines, but circles are not so easy to see in the Fourier space. You can see, if you would look really close, you could actually see that there would be concentric rings in here, but only if you look very closely and know what to look for. The hair, now again I'm fighting against the light and contrast, but here you could in principle see that there is a streak going this way and a streak going a little bit more along the y-axis. So maybe you could tell something. The peacock feather, well, you can in principle spot the 45-degree diagonal, but then there's a lot of fuzziness. So also the Fourier transform is not ideal to identify orientations in the image. So what we are going for is something called the structure tensor, which is the outer product of the two gradient vectors, and looks like this. And then all of a sudden we have 4 images instead of 1. But the problem again, the gradients are noisy. So what we do for implementation is we actually apply a Gaussian filter to each of the components, and then it's very nice. For this now I wrote this function, and I'm actually using a special feature of the Gaussian filter, so I get the Gaussian filtering and the derivative in the same function. That's a little trick which is quite useful if you want to do actually compute smooth gradients. Then the results I put here in different elements in a dictionary, and that is what we are going to use for the continued analysis. So looking at the components of the structure tensor, it looks, the J11 and J22 look very much as the gradient in x and y direction, which is natural. It's the absolute value of them, a little bit smooth. But the J12 and 21, there you can see first that you have positive and negative values, and you can also see that you have some orientations in it. This can be used now, all of them together, by doing some eigenvalue analysis, where we have, in principle, the structure tensor here in the eigenvalue problem, and we get 2 eigenvalues, lambda 1 and 2, which tells the energy in which each direction is working. And from that, we can start computing coherency. And that is the information, how confident we are about the information within a specific region or of a specific pixel. And that is looking at the max and min value of the eigenvalues over the 2. This tells us that when lambda max and min are about the same, it's a quite flat region. If there are a large difference between them, then we have some preferential orientation locally. And that is can also be computed without actually computing the eigenvalue for each pixel by using the structure tensor like this here. And looking at what and I also implemented the coherency function, so you don't have to do that if you want to use it. And now we can see, looking at the coherency of this ball packing, you can see that around the edges we have a lot of clear information, but outside where it's flat, okay, it looks a bit noisy, but essentially very low values in coherency. So that tells us as soon as we have edges, we want the information. The next thing is to look at the orientation, and that's, I actually don't show it here, but yeah, okay. It's the arcus tangens between, let's see, the sum of the 11 and 22 over the 21 and 21 squared, I think it was. But here now we have converted this image into an image where we have local directions. So this image actually shows you the rotation, local rotation of the structures. And that's a piece of quantitative information already. And now let's look at more textured images. Now we had just large flat regions and clear edges. But now let's look at this hair and the peacock feather, which are more textured. And well, the coherency is a bit tricky to get good values on. Apparently, we are confident about everything here. And looking at the local orientations, you can see that you have slightly negative angles here and slightly positive angles in this region, which actually makes sense because you see here it's tilting towards the left and here it's tilting towards the right. So we can actually locally see what the directions are. And this area is apparently a little bit more uncertain, but it says essentially that it's positive directions, but there is some blue mixed in it, but it's a bit hard to see in this slide. And you can also see that the average distribution of the angles is around 0. And the peacock feather, we do the same. Now you can see that the average orientation is now shifted towards about 45 degrees. And now if we compare the two together, first this one, that we have a general direction in this image, which is going left to right. And this one is the general direction moving towards the 45 degrees. Locally, so usually the global information is not so relevant. We want to know a little bit more locally what is going on. So now if we look at different regions of the peacock feather, we have 3 regions, and you can see in this region we are tending towards almost 90 degrees or something like 70 degrees or so. In this region, if you remember, we had more or less horizontal, then we have a 0. And in this region, we are something like 45 degrees. So go back to the image. Yeah, there it is. Here we had almost 90 degrees here, more or less 0 degrees, and here is 45 degrees. So we can actually locally determine the orientation in the image. And if we want to look at every region, I needed to write a little function for that. And the problem is that if I compute the local average, it's actually misleading. And the reason is, as you can see here, we have no clean distribution. It never goes completely down to 0, but we have a lot of bias of uncertain angles. And this bias makes it impossible to compute the average and get a reasonable value. My solution was to compute the maximum peak of the histogram and use that as the local orientation. And that is what this function is doing. You can study it if you like, but I put it here. And now looking at this, you can compute, first of all, the local angles. And then I need to do some processing here to compute the vectors, and then we can do a nice vector field showing the orientations within the peacock feather. So this is something you can use, for example, if you want to look at the fiber materials and see directions. You can also use it for texture analysis. So if you have images with different textures in them, so local patterns. Then you can also look at the local pattern orientations. Another application is looking at fingerprints, looking at the main direction in the fingerprint. So this is a way of quantifying images from images using filters as a base, and no further segmentation. You can just compute it out of that. The final thing is verification. And the question is, how good is my filter? What am I actually doing to the images? And one term that was coined by my former boss was data massage. And that is more or less you modify the images until they look like what you want to have them. That's not a good approach. And you can even, if you filter too much or modify too much, you can actually invent new features, and then you can imagine what happens if you try to quantify something out of those features. So techniques to verify the validity of your method is, first of all, look at them. Sometimes the eye doesn't tell a lie, so look at the images. Do they really make sense? Next thing is to work with differences. So you can do some modification of the data and take the difference between the original and the modified, and then you see, okay, I see structures, I see not structures, or something. And the last is to build into a framework where you actually apply the filter with different settings, with different signal-to-noise ratio, and sometimes you can actually use phantom images for doing this, and I call that a smoke test. So first thing, looking at the difference images, we have a noisy image, we apply a filter, and if you do the difference between the original and the processed, the ideal case, you would only see the noise. If you would do too much smoothing, then you will start seeing these halo effects in your filtered image, or in the difference image. If you would, in the filter kernel, apply some intensity scaling, so for example, you have a box filter and forget to divide by the number of elements, then you have an intensity scaling, so leading you away. The final one is that you can also see geometric shifts. So if you would use even-numbered filter kernel, then you would shift the whole image 1 pixel aside, and that would also be visible within the difference image. And that would be characterized by having both bright and dark edges around the image. Yeah. So that is a good diagnosis to see how well is your filtering actually doing. Then we have the smoke test. That would, as I said, put it in a larger framework where you play with different signal-to-noise ratios, you play with different filtered parameters, maybe even take one step further, going to doing some segmentation and see, do you actually get what you want under different conditions? And this, if you use phantoms, is easy to do repeat. So you repeat with same signal-to-noise ratio, but different noise cases, and you see how it happens. And then you can get some nice statistics and error bars and see how well you actually performed. And finally, you can results as a function of signal-to-noise ratio and see in which parameter range is actually my processing acceptable. So here is one case where you do it with a phantom, and the idea with a phantom is you have something with known features, and sometimes you can also play with the sizes or shapes, contrasts, and of course the noises. Here you have a classic phantom which is seen in, I think, every medical imaging lecture, is the Shep-Logan phantom. It should simulate what the brain looks like in a tomography, and the other one oops, where is it? Here. The other one is what I used in an example where I wanted to segment root structures. Here I played with some, call it artificial root network, and I played with different sizes, different contrasts of these branches in this root. You can also use data for label data, and then you can use some real data, which is labeled by, and you can use it for validation of training models and testing, and that we will talk about a little bit more in next lecture. And when you work with gray levels and want to verify how good is it, then you need to use some kind of metric, and the most used one is the mean squared error. And another one is structural similarity index, which is a bit more complicated, and it was developed to check the quality of transferred images and videos. And there you can have a quite good idea of the correlation and similarity of images. And it's actually, that one actually is also sensitive to intensity changes, it's sensitive to blurring, and so on. So here was a test example where I played with these different sizes, different signal to noise ratio, and that I run my system and plotted the results, and I could see clearly that under some conditions with very thin roots, it failed pretty quickly, but with larger roots, it could process much better. So here you can see in what ranges of sizes in the image that you can work with, and also which range of signal to noise ratio. And that brings us to a little summary. We have looked at very many different filters today. Here I have a matrix of all the main filter types and a different signal to noise ratio. And looking at the finer details, the cross in the middle, this one, little cross here, you can see what the effect is under different signal to noise ratio conditions. So actually this one is really bad, and here you can see what the different filter types can do to them. Of course, in this case you can't expect to have extremely sharp edges, so there is of course some signal loss, but some filters do less good than others. And that brings us to the end of today's lecture. So we have looked at very many different types of filters in different domains, and how you can process these images depends on what is your purpose with the data. So then you have to decide, do I just need something that I can clearly segment, or do I want to maybe look at fine details in it based on the gray levels? That also decides what kind of filter you want to use in the end. And it's also a question of available time, because some filters can be done in no time. Others, you have to be a bit more patient. Maybe it takes a couple of hours for it to process the image, for a single image. And then maybe if you have 1,000 images, then you have to think about, do I have the time to process these? And a good point is that we can do a lot of filtering, but it's always better to have a good image from the beginning. So don't remove, think that you can skip over a couple of steps because you can do filtering anyway. So try to optimize the image acquisition as much as possible with a given time for the experiment, and then do the filtering necessary. Good. That was the end of today. And